Hello, everybody. I'm Andrei, and I work for JetBrains as a Senior Vice President of Investments, Research, and Education. Welcome to Regionals. Great things happen when great minds come together. JetBrains wants to seek out great minds all across the globe, support their initiatives, and work together to create great things that will make the world a better place. That's why JetBrains is proud to be a global tool sponsor of the ICPC. There are already many great minds working at JetBrains, and together we have created some amazing things, like the Kotlin programming language, for example. It keeps on growing and growing in popularity. In 2017, Google began officially supporting Kotlin as a language for writing Android applications. We have also created professional development tools like Cline for C++ programmers, IntelliJ IDEA for Java, PyCharm for Python, and also educational tools that help people learn and teach programming. The regionals are the biggest contest in the ICPC calendar. Thousands of talented people all over the world team up to solve complex real-world challenges. These contests are the proving ground for future champions. But even if you don't make it through to the finals, the experience of competing in the regionals and the new friends you'll make along the way are priceless. Enjoy the ride. Best of luck to everyone.
First of all, before starting, as I said, this was the largest regional conducted, and there are lots of team, around 4,300 teams. And so at the start itself, we expected a really high load, and it did not disappoint. The load was really high, even more than what we planned. But luckily, due to all the planning that I and Deepa did, we were able to handle even the higher load than expected during the contest. So for some stats, there were around 84,000 total submission. So the submission shown on the contest page just shows the full submission, but the judge, of course, has to evaluate all the sample and custom submission too. So including all that, there were around 84,000 submissions, which is a lot. We were getting, at certain points, we were getting constantly at 100 per second, 500 per second. At one point, we thought it was going to around 250 and so on. So that was the high amount of load that we were expecting. And so let me just go into how the architecture of the platform is. And the reason I'm telling all the details is that most of you would be participants in competitive coding, and most probably in future you'll be a software engineer working in companies. And these are all the things that go into making a high scale platform. So hopefully you will find it useful. So here's the system architecture of Codedrills, and it's like a pretty standard one. This is what most high scale or high load sites have it. So first there is always a proxy or a load balancer, which is what you connect to when any API call is made to Codedrills, and it handles or it passes on all the requests or anything to the server, and whatever response comes. So everything goes via load balancer, and then there are the servers themselves which perform all the logic. It has the actual logic, and they of course store the data in a DB. We use MySQL, and for optimization and load handling, we also use a cache. We use Redis. Now the important part is the worker queue. So when you hear of submission queue, this is what happens. Whenever a submission comes, the server first divides this into small tasks. So running a test case could be a task. So there might be 10 test cases for a particular problem submission. So all these are queued in the request queue, and there are a bunch of worker nodes. And these worker nodes would then execute that request, and whatever the response is, say maybe there's a runtime error, or maybe the time limit or maybe limit exceeded, or it did complete successfully and produce an output. All these, whatever the result is, it puts it back to the response queue. And then finally, like the server again looks at the response and calculates the overall. So say all the test cases are passing, then it would mark the submission as accepted and calculate the time or memory limit taken. So yeah, I hope that was pretty straightforward logic generally. But the interesting thing, so all these are like, if you think about it, pretty straightforward so far, but it becomes very interesting when you have to do this at high load, when there are thousands of requests pending, or when at the start of the contest, when there are 50, 60,000 people, 50, 60,000 pages all being loaded simultaneously. So you have to be very careful about how you do, or what are the code, how, which part you cache, which part you don't, and so on. So before going that, I will just go into one particular detail of how exactly a submission is processed. So a submission is processed in Codedrills by, like, it's first broken up into a bunch of tasks. One task is to just compile it. So the compile just runs the compile command. So all of these are done in Docker, so that we can support any language or anything easily. So first the compilation is done, and so how this works is, again, we put the compile task in the request queue, and the worker node compiles it and puts the result in the response queue. And once the server function or the compilation was successful, it will now fan out all the test cases. So the test cases itself has two parts. One just runs the program against the test input and produces the test output. The other is the checker or verifier for that, which verifies whether the output produced by the user program matches with the one that is the expected test case, which is uploaded by the setter. And finally, when all of them are done, we finally compute the result itself. So this is our typical. So it's like a common thing across all online judges. This is our typical program is evaluated. Now, before talking about the exact optimization, so I will give a high level overview. So the types of optimization that is required for handling high load. First is code level optimization. So you might have that we should not make a lot of DB calls, and we should not make a lot of fan out requests, and so on. So that is the first level of optimization, code itself. And the second level would be to tune the parameters of a single instance. So the goal behind that is, if there is a single instance of server running, what is the maximum QPS that can be supported by that server? And what are all the bottlenecks for that? And we have to carefully tune and make sure that so as we add more resource, the number of QPS supported by one server also increases. And finally, even one server is generally not enough if the load goes very high, like we expected for the preliminary round. So for that, we now need to handle multiple servers. Now, adding multiple servers comes with its own set of challenges. It's not just as easy as just adding more instances running. So I will talk about all the three levels of optimization. So in scaling code, like I said, the main aim is to, I think this will be the most familiar to competitive coders, because we, at some point of the other, we have some solution which is timing out and we try to optimize it. And it's very similar to that. So the types of thing that is done. So first is pagination. This is to keep the request response bounded. So one example is the teams page in the contest. So earlier we did not paginate it. So every time you call it, all the teams uh, uh, were fetched and written. Now that won't work if we have 3,000, like 4,500 teams. So what we did was we paginated it. So only one page was fetched at a time. So that puts a bound. We know that at any point of time, more than 100 teams can't be displayed, and that like makes things very easy. And the second is fan out call. So as you can imagine, the scoreboard is the most complex part apart from the judging queue itself. It has to calculate the score, and it has to populate the name of the team and what is the penalty, and add links to that, and it has to do it in a live contest very frequently, so that there's a reasonable liveness. So we can't say that we are updating every half an hour. It has to be like every 30 seconds, every 1 minute. So scoreboard was a very critical and complex part of that. The one thing in scoreboard we observed was that there are a lot of fan out calls. So just to display the scoreboard, we fetched all the ranks, and then we have to fetch all the team names and the link to their team, as well as all the problem submission links and all. So that's one of the first thing we optimize. So how we optimize these things is we cache the end result itself. So say every 30 seconds, we can compute the scoreboard and also fetch all the things that is required to display them, and then just cache it. And whenever a request comes, we just fetch it from the cache instead of calculating it again and this. And this makes everything blazing fast, because you don't need to compute at all. The only task that is done in that request is just fetch from the cache and return. So that's what it. And the other thing is that we always look to cache in front end also. So one example of this is the editor preference. So you can, if you have used the site, you know that we can select what is the editor background color, key bindings, etc. Now, earlier we fetched it on each page load, but that's not really required. So we started caching it in the front end and avoiding the API call to backend. And the final thing that really helped was optimizing DB queries. So there are a lot of queries to the database, and we looked at each query and made sure that so there's this command called explain, which shows which indexes are used, and we made sure that all the proper indexes are being used, and if not, we added the index. So this was the thing. Now I will also give one particular example. Even after doing all this, what we observed was that while it was handling load properly, a particular submission was taking a long time. So for example, even apples and bananas, which is the simplest problem, even the sample submission for that used to take around 5 seconds without any load when there was no load. So that was like simply not okay for us. So what we did was we first like tracked down what all part were causing this delay. So one thing that is always unavoidable is the round trip time from the browser to the server and back. Now excluding that, everything was in our hand. So what we observed, first thing we changed there was that how it used to work earlier was there used to submission used to be made, and then every 2 seconds we used to fetch the status of the submission, and whenever it was completed, we used to display it. So there was a 2 second gap there. So even though the server was finishing fast, the it was not displaying in the front end for 2 more seconds because that's how long it took to fetch it. So that was the first thing we optimized. Instead of fetching every 2 seconds, we did a standard technique called long polling, where we just browser just opens a connection to the server and keeps it open. And whenever we have completed the submission evaluation, it just sends back the result. So as soon as it's completed, it sends back. So there is no 2 second delay. And we also did a bunch of others, all the optimization that I mentioned here, caching the problem, test cases, etc., etc. But even after that, we found that it was still taking around maybe like 2 seconds. Even though like 2 seconds would have been good enough, we wanted still faster. So we dug into really into how where exactly the time was taking. So the reason was that to see a simple apple and banana submission would take just 80 milliseconds of actual execution time. And even excluding the RTT, where exactly did the 2 second come from? So if you recall the how exactly a submission is evaluated, we notice that so each submission has all these tasks, right? And all this for every task, it has to be added to the queue, and the worker will evaluate it and add to the response. When we trace where exactly each submission is taking time, we notice that the actual most of the time was spending in adding to the queue. So the queue is a distributed queue. Since we can't, it has to guarantee that if it sends an acknowledgement, it will deliver the task. Otherwise, we will have some lost submission. So now, by the nature of distributed queue, it is high latency. So we observed that each time we added to a queue, there was a latency of 300 milliseconds. Now, if you see for a simple sample test case, there is only one test case, but there are three tasks for that: compile, running the test case one, and checking the test case two. And each task we were adding to the queue 2 times. So that means that each task was taking 600 milliseconds just being waiting for acknowledgement from queue. And there are three tasks, so 1.8 second there itself we are spending. And so what we did was that I think it would be pretty obvious by now was combine all these tasks. So the first thing we did was combine the run and check so that the same worker node will process both running of the task and checking of that. That also had some unintended effect of good effect of caching all the result in that worker node itself. And this also reduced the amount of time each test case wait for the queue. So now for a simple apple and banana, we only have two tasks, which is compile and run and check test. So that reduced it to around easily to around 1.5 seconds. But of course, like any good coder, we felt that even that was not enough. Could we do better? So especially for larger test cases, right? So if there are multiple test cases, then what? So we reduced even that by doing some batching of across test cases itself. So we might have like bundle a group of test cases and evaluate all of them in a single worker node, thus again reducing the amount of time spent waiting for the queue. This was especially useful for our interview problems because in interview problem, we don't have the concept of test case per number of test case per file. Rather, it's only one test case per file. And to cover all the edge cases, we had like 30, 40 test cases per problem. So all this batching and all really showed the effect here. And also for competitive part, especially at high load, this really optimized the amount of time a particular user had to wait. And but even after that, we felt that it took around 1.2 seconds or so, and even that we were not really satisfied. So we again tried to bundle more, and at the end, so for a simple submission, this was the case for any sample submission, and for the first one or two problem in the regional, all the things were bundled into a single task. Like it will compile, it will run the test case one and run the test case two, and compute the result and do that. So all of this then made sure that we were only adding to the queue once. So the entire batch is a single task, so it's being added to the queue once, and worker will process all the tasks and add it back to the. Now you might ask, like, why not do this for everything? Then that would actually like counterproductive, because adding a lot of test case to a single worker node will cause that to run for a long time. So especially consider, say, languages which have a time limit multiplier, Java or Python. So those take a long time to process one test case. So if everything is run one after the another on a single worker node, then it will take a lot of time. So we, after some tuning, we decided that two per batch was the optimal one. So that's what we did. And after doing all this optimization, we found that simple submission took less than 1 second, which is what we wanted. And finally, like, we were happy with the result. I think if everything was fine, the internet connection was well, and all the caches were loaded properly, then it took around 800 milliseconds for a simple submission from end to end, like from the moment a user pressed submit to the moment they saw the result. So so I just like this, I went into detail just to give an example of how one particular area we looked into detail and optimized. Like this, we did for a bunch of areas, scoreboard, teams, and everything. And one more optimization that was really useful, and it was actually suggested by a lot of people and our judges, was to skip uh, submissions if some earlier test cases fail. So if in a batch, one of the earlier test case failed, we just started skipping it, and it really helped a lot, especially in TLE. So if you think that TLE was the hardest cases generally because it took up all the time that was allotted to the worker. And if you have a large submission in Python and with a large time limit problem, they would take up like 10-15 seconds of the worker. And in that time, that worker node could not do any other work. So adding this skip really improved the performance for large test cases. So that was for the level one coding. I will quickly also go through the other two instances. I won't go into full detail. The For a single instance, the main thing was finding a bottleneck. So usually what happened is you would expect just increasing the CPU or increasing something would increase the QPS that is handled by that server. Unfortunately, that's not the case. And the reason for this is called bottleneck resources. So there are a bunch of resources, all of which should be at the optimal level for the QPS to be high. So by resources, what I mean, the resources, for example, in our case, are the CPU, memory, server threads, and DB connections, and the cache connections. So all of these have to be properly tuned. So for example, we can't just say that have 1,000 of each also. So for example, if you say have 1,000 server thread and we have only 4 CPU cores, that would mean that majority of time is just spent uh, in context switching between the threads. So we have to be careful about the exact number of threads. It can't be too low. If it is too low, then that means the CPU is not being used optimally. So for each of these resources, we performed careful load tests and tuned the exact optimal number of each of these resources for that particular instance. So once we done that, a single instance was fully optimized. And but yeah, even then, like I told, a single instance can't handle a large amount of load, and also it won't be resilient. Say one single instance goes down, then what will happen? The entire site will go down till we restart it again. So for all of this, the next part comes in where we just add multiple instances. Now, ideally, this should be easy just adding, but in practical, there's a lot of issues around this. The main thing around this is concurrency issue. So say, for example, so as if you recall the how an submission is evaluated, there are multiple tasks for the same submission. Now, what happens if the result for these tasks goes to different instances? So earlier, when we just naively added instances, there was some issue where that there was a race condition between updating the submission result by two different server instances. So all these issues had to be handled for us to support multiple instances. And of course, like the how we handle that particular error is using transactions, making sure that we open the transaction with DB and only then updated and then close, so that if there was a conflicting update at that time, that was denied. And this especially scaling multiple instances, especially critical for worker nodes. So the ideal way this would work is called linear scaling. So it would just mean that say you could support 1,000 QPS for a server, and if you add one more server, then it should ideally support 2,000 QPS. Now, due to other resources or other bottlenecks, this might not always be possible. So that was what we were doing at the end to make sure that if by just adding a new instance, we would be able to handle more load. So this especially for worker nodes, we wanted to ensure that if the queue started building up, then all we had to do was to increase the number of nodes and it should be able to handle it. So there was a lot of work that went into doing that, because then DB usually became the bottleneck, because DB instances, we just wanted to keep one. We did not want to shard or anything, because that usually becomes too complicated. Instead, like we managed to do everything using this one instance by carefully ensuring that we don't write to DB often. So yeah, I think like these are all the things that go, but we didn't just do this in a vacuum. So we always had load tests. So what load test does is that uh, we just have a bunch of user and all of them virtual user, all of them bombarding the server with the expected QPS that we had. So we already know what would be the expected number of teams, and we estimated the number of users that would be there. And we had to ensure that that particular user and that particular number of QPS would be handled. So we built load test for that. And using that, we did all the optimizations that we spoke earlier. So there are like a bunch of optimization which are still pending, but those were not really needed because it was still handling the load. So this was our main thing for testing whether optimization was needed or not. And as you can see, the first time we got this load result was the time when we were really confident that we would handle the load. It was, I think, uh, 40 or 50th time we were running this load test, and it was during that time only, like finally when everything fell into place, everything was optimized, and there were zero request failures if you see, and the average response time was below 500 milliseconds for 5,000 users. So yeah, like that was it. So these are all the things that usually go into it. Of course, like these are not in a vacuum. While I and Deepa were working on the code and everything, there were a lot of inputs from other people. I would like to thank the whole of our judging team who always gave all this input, all this micro optimization, especially Vichitra, Ashwin, Kevin, etc. All of them helped a lot in making sure that the worker were secure. It was handling good load. I think like, yeah, that's all that I had for the optimization part.